It's funny. I used to think two-stroke engines were kind of, well, crude. I mean, it's so simple, right? But the power they can crank out, it's amazing. It really surprised me.
Yeah, the simplicity can be deceptive. I mean, even engineers who've worked with them forever, real experts, they've been blown away by just how much performance you can squeeze out of them. And not just power, but reliability too.
Totally.
Yeah.
And that's kind of what got me hooked on this deep dive you sent over
Yeah.
about tuning these things. It's like there's this whole world of optimizing these seemingly simple engines. So today we're going to try and break down some of that, the core principles, right? Not get bogged down in every little tweak, but really understand the why behind it all.
Yeah, think of it like instead of just memorizing a recipe, you're learning the chemistry of cooking. You get the fundamentals, you can really start to improvise and experiment.
Love that analogy.
Yeah.
So your material is super comprehensive. It's got everything from like the cylinder head, how the gases move in and out, the exhaust, the fuel mixing, the spark, even keeping everything cool and lubed up. But one thing that really jumped out at me right off the bat was this idea of blueprinting.
Ah, yeah, blueprinting. It's essential, really. You see, even a brand new engine straight from the factory, it's not always perfect. There are these manufacturing tolerances, little variations, and sometimes, well, they can be a bit bigger than what's ideal for getting that peak performance.
So it's like, even before you start messing with performance mods, you need to make sure the engine's actually built right, to spec. Like in the material, there were some pretty crazy examples of factory inconsistencies. I mean, piston clearances way off,
Yeah.
connecting rods of different lengths in the same engine.
Oh, yeah, I've seen some wild stuff too. Crankshafts that weren't perfectly aligned, squish clearances all over the place. It's really eye-opening.
And the thing is, I get it. Manufacturers, they have to design for a lot of different users, different conditions, and they got to keep costs down, right?
Yeah. Right. Compromises have to be made. But for someone who's really after performance, those compromises, well, they can be the first things to go.
So blueprinting, it's all about finding those little imperfections and correcting them, building that rock-solid foundation before you go any further.
Exactly. You start with a good base, then you can really start to fine tune and get some serious gains.
So let's get into some specifics. Starting at the top, literally with the cylinder head. Now, it might seem like it's just a lid, but it's actually way more important than that.
Oh, it's crucial. It's where the whole combustion party happens, right? And the shape of that combustion chamber features like the squish band. That's where things get really interesting.
Squish band. Okay, now that's a term I've heard thrown around, but not everyone might be familiar. Can you break down for us?
Sure. So the squish band, it's basically a part of the cylinder head that's designed to be super close to the piston crown when it reaches the top of its stroke. Creates this really fast, tight squeeze of the fuel air mix.
So it's forcing that mixture towards the center, right before the spark plug ignites everything.
Exactly. And this does a couple of really cool things. First, it helps to cool the piston, which is super important because things get crazy hot in there. Second, it creates this turbulence, mixes everything up really well, makes the burning more efficient.
And the source even talked about how the bore and stroke, the dimensions of the cylinder, play into this whole squish design.
Right. The ratio between the bore and the stroke affects how much of the piston crown is actually exposed to the direct heat of the combustion.
Mhm.
So, like an engine with a longer stroke compared to its bore, it tends to have a smaller combustion chamber, less surface area for the piston to get hammered by the heat.
So that can actually help with reliability and prevent warping, right?
Exactly. Now, speaking of things that can go wrong, we got to talk about detonation. That's a real engine killer.
Yeah, detonation sounds pretty bad. What exactly is happening when that occurs?
Well, basically, it's like a second uncontrolled explosion happening after the spark plug fires. The pressure and temperature in the cylinder spike too high, and boom, the remaining fuel air mix just goes off.
And there's some pretty clear signs if you're looking for them, right? Like a piston crown that looks sandblasted, damage to the cylinder bore, spark plugs cracking.
Yep, all bad news. If you see any of that, you gotta back off and figure out what's causing the detonation before you melt a hole in your piston.
Now, back to squish clearance for a second. The material really emphasized just how critical this tiny gap between the piston and the head is. I mean, even a tiny increase can mean you're just wasting fuel and power.
It's crazy, right? You'd think a little extra space wouldn't matter much, but it can make a huge difference. They even gave an example, a Yamaha TZ250, where a clearance that's not uncommon from the factory could mean you're losing almost a quarter of the fuel charge.
Wow, that's a lot of power going down the drain.
Right, and it's not just wasted fuel. It's fuel that's not contributing to pushing the piston down at the right moment. So getting that clearance right is key to getting the most out of your engine.
And thankfully, the source gives some specific guidelines for different engine sizes. Plus, they explain how to measure it using modeling clay. A pretty clever trick.
It's a classic technique, simple but effective. You can get a really accurate measurement that way.
So you know your squish clearance. What's next?
Well, the angle of the squish band matters too. That affects whether you get more power at low RPMs or higher up in the rev range.
Interesting. So depending on what kind of riding you're doing, you might want to tweak that angle a bit.
Exactly. It's all about tailoring the engine's characteristics to your needs. Now, another big one is compression ratio. Most people know what that is, but the source gets into some nuances, talking about uncorrected versus corrected compression ratio.
Right, so uncorrected, that's just the basic volume ratio, top to bottom.
Right.
But the corrected one, that takes into account when the exhaust port actually closes, right?
Exactly. It's a more accurate way to look at the effective compression because the cylinder isn't really trapping the mix until that exhaust port is sealed by the rising piston.
Makes sense. And there are formulas to calculate both, factoring in the bore, stroke, and combustion chamber volume. They even walked through a whole example with the Suzuki PE175.
It's not rocket science, but it is important to understand what those numbers mean and how they affect performance.
So I guess the takeaway is more compression doesn't always equal more power, right? It's got to be balanced with the fuel you're using and what kind of power band you're aiming for.
Exactly. You can get great mid-range boost and a wider power band with higher compression, but push it too far, and you're back to Detonation City.
And that's where the fuel's octane rating comes in. Higher octane means it can handle more compression before things start going boom.
Exactly. It's like the fuel's resistance to knocking, to that uncontrolled explosion. So higher octane lets you run higher compression safely, which translates to more power.
And the source even gave a rule of thumb for how much you can safely increase compression when switching to a higher octane fuel. Pretty handy.
Definitely good to know. And then there's the head gasket. It might seem like a small detail, but it can actually affect your compression ratio too.
Yeah, and they even talked about some racers who ditched the gasket altogether, just meticulously mating the head and cylinder for the absolute best seal.
It's all about squeezing every last bit of performance out, minimizing any leaks. And of course, using the right sealant is key, especially when you're dealing with those high temperatures.
All right, we've spent a lot of time up top. Let's move down a bit. Now, getting the fresh fuel air mix into the cylinder and the burnt exhaust out, that's a whole other story, right? Porting and scavenging, it's where things get really intricate.
This is where the two-stroke design gets really clever. It's all about timing and flow. And you got to give credit to Adolf Schnurl, his loop scavenging method. That was a game changer.
So before Schnurl, what were they doing? I mean, how are they getting the gases to move the right way?
Well, they use these things called deflector dome pistons. Basically, the piston had a bump on top to try and direct the fresh mix upwards, away from the exhaust port.
Sounds kind of clunky.
It was. It worked okay, but it had some big downsides. The deflector created more surface area for the piston to heat up, so power was limited.
Yeah.
Plus, the flow wasn't that efficient.
So Schnurl came along and basically flipped the script, right?
Yeah, he ditched the deflector and came up with this system using a single exhaust port at the back and two transfer ports on the sides. These transfer ports were angled so the fresh mix would swirl around, creating this loop flow that pushed the exhaust out.
Ah, so like a mini tornado in there, getting those gases moving the right way.
Exactly. Way more efficient, and it allowed for much higher power outputs, really revolutionized two-stroke design.
But it didn't stop there, right? Your material talks about other types of ports, things like auxiliary exhaust ports and boost ports.
Right. As they pushed for more power, they found that just making the main exhaust port bigger wasn't always the best solution. It could kill the low-end and mid-range power.
So these extra ports are like a way to fine-tune the flow at different RPMs.
Exactly. Auxiliary exhaust ports, they basically open up at higher revs to let more exhaust out without messing with the low end. Boost ports do a similar thing, but for the incoming fuel air mix.
Clever. It's like they're finding ways to cheat the system, get more in and out without compromising the power band.
Totally. And then there's the exhaust power valve. That's a real piece of engineering ingenuity.
Yeah, I've heard about those, but how do they actually work?
So imagine a valve that can change the height of the exhaust port. At low RPMs, it's partially closed, which improves low end and mid-range. Then, as the revs climb, it opens up, giving you that top-end boost.
So it's like having two exhaust ports in one.
In a way, yeah, it's pretty cool. Yamaha really pioneered this with their RD and RZ bikes, and the results were amazing. You can really see the difference in the power curves.
So we've talked about different types of ports, but what about actually modifying them? Like if someone wants to get their hands dirty and try some porting themselves, what do they need to know?
Well, first of all, it's not something to jump into lightly. You can definitely mess things up if you don't know what you're doing. But if you're careful and understand the principles, you can make some real improvements.
What kind of modifications are we talking about?
Well, for the exhaust port, widening it, making it more oval shaped, things like that. But you gotta be careful not to go too big, or the piston rings could snag and break.
Ouch, that sounds bad.
It is. Also, you need to make sure there's enough material between the exhaust port and the transfer ports. Otherwise, you'll get too much fuel-air mix escaping out the exhaust before it burns.
So it's a delicate balance trying to get more flow without messing up the whole system.
Exactly. And the shape matters too. Like when widening the exhaust port, you want the center to be slightly higher than the edges.
Why is that?
It's to compensate for the piston rings. They tend to bulge out a bit as they move up and down, so shaping the port that way helps to maintain a better seal.
Ah, I see. It's all about those little details, isn't it?
It is. Now, if you want to get really technical, you can actually calculate the exhaust duration, which is how long the port is open in terms of crankshaft degrees.
Yeah, the source goes into that, even using a Morbidelli 125 Grand Prix engine as an example.
It's pretty cool. You can really see how those numbers translate into engine characteristics.
Another thing that surprised me was how much the shape and surface finish of the ports matter.
Oh yeah, it's not just about the size. Smooth flow is key. And the source mentions that the carbon deposits can actually tell you a lot about how the gases are moving.
Really? So you can actually see where the flow is good or bad just by looking at the carbon buildup.
Exactly. If you see an area that's clean while the surrounding areas are covered in carbon, it often means the flow is messed up there, creating turbulence.
So you might need to reshape the port to smooth things out.
Exactly. Sometimes a little grinding can make a big difference, and in some cases you might even need to weld and reshape the whole port for optimal flow.
Okay, let's talk about something that's often overlooked. Crankcase compression. I think most people focus on what's happening above the piston, but the crankcase plays a big role too, right?
Absolutely. In a two-stroke, the crankcase acts as a kind of pump, pushing the fresh mix up into the cylinder. So the compression down there is important.
And I remember reading about old school tuners stuffing the crankcase to increase that compression.
Oh yeah, the stuffers. It could work, give you more top-end power, but it often made the power band super narrow and peaky.
So, not always the best solution for everyday riding.
Probably not. Now, when it comes to the transfer ports, things have evolved a lot. There's this technique called staggered porting, where the ports open at slightly different times.
And that's to improve the flow across a wider range of RPMs, right?
Exactly. Some ports handle the low and mid-range, others kick in at higher revs. It's a clever way to keep the engine breathing well throughout the power band.
And modifying the transfer ports, it's not just about making them bigger, is it?
Nope. Shape and smoothness are crucial. You want to remove any rough edges and make sure they flow nicely into the cylinder. Even the cutout in the piston skirt below the gudgeon pin, that's part of the transfer system and needs to be shaped right.
So it's like a whole interconnected system. Everything has to work together.
It is. Now, how that fresh mix gets into the crankcase in the first place, that's determined by the inlet port timing.
Right, so that's about when the port opens and closes relative to the piston's movement.
Exactly. And this affects where you get your power, low down or up high. Longer inlet durations, they tend to favor higher RPMs.
And there are a couple of ways to control that timing, right? Piston porting and rotary valves.
Right. Piston porting is the simplest. The piston itself uncovers and covers the port. Rotary valves are more complex, but they offer much finer control over the timing.
The source actually pointed out some common manufacturing issues with rotary valves, like pulley-shaped ports that restrict flow.
Yeah, it's amazing how often you see that. The factory port isn't always ideal, so smoothing things out and matching the port to the rotary valve disc, that can make a big difference.
And sometimes you even need to adjust the timing of the rotary valve itself, right?
Sometimes, yeah. It can involve moving the valve cover or even modifying the drive hub. Pretty intricate stuff.
And then we have reed valves. I know they're common on smaller engines, but what's their main advantage?
Reed valves are great for low-end and mid-range power. They basically act like one-way doors, letting the mix into the crankcase but not back out. This helps to maintain a good charge, especially at lower RPMs where the pulses in the intake aren't as strong.
And the source compared them to just increasing the size of the transfer ports, saying that reeds are better for low end, while bigger transfers favor top end.
Exactly. It's about choosing the right tool for the job, depending on what kind of power band you're after.
Now, what about this power porting thing? That sounds pretty interesting.
So power porting is when you modify the bottom of the piston skirt, basically creating a cutout to increase the duration of the inlet port opening. This can give you more top end, but it can also sometimes hurt the very low end, especially on older designs.
Interesting. So it's like another way to tweak the timing without getting into more complex valve systems.
Exactly. And finally, there's case reed induction. This is where the intake goes straight into the crankcase rather than through the cylinder wall.
And that gives you more freedom with the boost port, right?
Yes.
Because you don't need that space for the traditional inlet port.
Exactly. It's a great system for high-performance applications, especially with the advancements in reed pedal materials.
And speaking of reed pedals, they talked about different types, like phenolic and poison reeds, and how they can affect performance.
Yeah, you can really fine-tune the reed system by choosing the right pedals and modifying the cage. But they warn about bad practices that can lead to reed flutter.
What's reed flutter?
Basically, it's when the pedals don't seal properly at high RPMs, which messes up the flow and kills power. So you got to be careful how you modify things.
All right, I think we've covered all the ins and outs of getting the gases moving the right way. Now let's talk about something that's synonymous with two-strokes, the expansion chamber, or as most people know it, the tuned pipe.
Ah, the tuned pipe. It's a thing of beauty, really. Not just about muffling the noise, but actually harnessing those pressure waves to make the engine run better.
So how does it do that? I mean, it's just a pipe, right?
It's all about the shape and the way it manipulates the pressure waves created by the exhaust. It's like a carefully choreographed dance.
Okay, break it down for me. How does a tuned pipe actually make more power?
So imagine this. The exhaust pulse leaves the cylinder, goes down the header pipe, and hits the diffuser, which is a widening section. This causes the pressure to drop, creating a negative pressure wave that travels back towards the cylinder.
Okay, so a low pressure wave heading back towards the cylinder. Then what?
Well, that negative wave arrives just as the transfer ports are open, helping to suck out any remaining exhaust and pull in more fresh mix. Then, the pulse hits the reverse cone, a narrowing section, which increases the pressure again.
So now we had a high pressure wave heading back.
Exactly. And this one arrives just as the piston is starting to compress the new charge, forcing even more fresh mix in and preventing it from escaping back out the exhaust port.
It's like you're using the exhaust's own energy to supercharge the intake.
Exactly. And all the different parts of the expansion chamber, the header, the diffuser, the belly, the baffle cone, they're all carefully designed to time these waves perfectly.
And of course, we can't forget about those exhaust power valves. They're basically changing the shape of the exhaust tract on the fly, further tuning those pressure waves.
Right. Yamaha's YPVS, Honda's ATAC, they're all about getting a wider power band by controlling the exhaust flow at different RPMs.
So if you're thinking about designing or modifying a tuned pipe, there's a lot to consider, right?
A lot, yeah. The length of the header pipe, the taper angles, the size and shape of the diffuser and baffle cone, it all matters. And there are formulas to help you calculate these things based on the engine's specs.
And if you're adapting a pipe from another bike, you got to be super careful how you modify it, right?
Absolutely. You can easily mess up the tuned length and the wave timing if you don't cut and weld it correctly. It's not just a matter of chopping it shorter.
So it sounds like a lot of trial and error, a lot of testing to get it just right.
It can be, yeah. But when you see the difference a good tuned pipe can make, it's pretty amazing. Like the source showed these two different pipes for the same Kawasaki engine, and the power curves were night and day.
Yeah, and they also mentioned how those dips or flat spots in the power curve can point to problems with the exhaust tuning.
Right. If you see a dip, it could mean the wave timing is off or there's some resonance issue. Dyno testing and tweaking the header length are usually the ways to diagnose and fix those problems.
And then, of course, there's the mounting and sealing. Any leaks in the exhaust can throw everything off.
Definitely. Got to make sure everything's tight and sealed, no gaps. And regular maintenance is key too. Got to keep that carbon buildup in check.
Okay, we've followed the air and fuel all the way in and the exhaust out. Now let's talk about how that fuel actually gets metered and mixed, the world of carburation.
Carburetors, they're kind of like the chefs of the engine, making sure the fuel and air are perfectly blended.
So what are the main parts we need to know about?
Well, you've got the float bowl, which keeps a constant supply of fuel. Then there are the jets, the main jet, needle jet, pilot jet. These all control how much fuel flows at different throttle openings.
Then the metering needle that works with the needle jet, right?
Right, it's like a tapered needle that slides up and down in the jet, controlling the fuel flow as the throttle opens.
And the throttle slide itself, that's what the rider controls to let more or less air into the engine.
Exactly. Now, the way this whole thing works is based on airflow and pressure differences.
Okay, explain that.
So, as the air rushes through the carb, it goes through a narrow section called the venturi. This creates a low-pressure area, which sucks the fuel up from the float bowl and into the airstream.
Ah, so it's like a vacuum effect.
Exactly.
Huh.
And the shape of the venturi, the size of the jets, the position of the needle, they all affect how much fuel gets mixed with the air.
And the source mentioned that early round slide carbs could have issues with turbulence, which messes up the fuel metering.
Yeah, those big cavities under the slide could create swirling airflow, making the mixing inconsistent, especially at low throttle openings.
So that's why they came up with flat slide carbs, right?
Exactly. Flat slides create a much smoother airflow, resulting in more precise fuel delivery and a nicer, more linear power band.
Okay, now we got to talk about air-fuel ratio. What's the magic number we're aiming for?
Well, it's not exactly a single number. It depends on a lot of factors. But the goal is to find that sweet spot where you get the most complete and efficient burn.
So too rich, you're wasting fuel and power. Too lean, you risk overheating and detonation.
Exactly. And the expansion chamber, how well it's working, that affects the optimal mixture too.
So if the pipe is doing its job, you can often run a leaner mix at high RPMs, right?
Right, because the scavenging is more efficient, you're getting a better fill of fresh mix. But at lower RPMs, you might need to richen things up a bit.
And they cautioned against using a carb that's too big for the engine. What's the problem with that?
Well, a big carb might seem like a good way to get more flow, but if it's too big, you won't get a strong enough vacuum signal, especially at low revs. This means the fuel won't mix properly, and you end up with poor low-end and mid-range performance.
So bigger isn't always better.
Nope, gotta match the carb to the engine's needs. Now, the source goes into some details about Mikuni carbs, like the different types of needle jets.
Yeah, P-type for piston port engines, B-type for rotary valve, and four-strokes.
Right. The B-type has more air bleeds to help atomize the fuel better, which works well with those types of intake systems.
And then there are the metering needles themselves, with all those codes that tell you their taper and length.
It's a whole science in itself. By choosing the right needle, you can really fine-tune the fuel delivery at different throttle positions.
And the source even walks through a basic carb tuning procedure. Start with the main jet for full throttle, then the pilot jet for idle, then fine-tune with the needle for the mid-range.
It's a good starting point. And they stress the importance of reading the spark plug, looking at the color and condition to see if you're running rich, lean, or just right.
It's amazing how much you can learn just by looking at that little spark plug.
It's a valuable diagnostic tool. Now, one thing they really emphasize is that carburetor tuning isn't a one-time thing. You got to be willing to adjust for different tracks, different weather conditions, even different riding styles.
Right, because air density plays a big role. Hotter air is less dense, which means less oxygen for combustion, so you might need to richen the mixture.
Exactly. And there are tools like RD meters that can measure air density, and formulas you can use to adjust your jetting accordingly.
So it's a constant game of adaptation, always fine-tuning.
It is. Now, even the airbox and air filter can have a big impact on how the carb works.
Yeah, they talked about the Suzuki RG500 that got a good power boost just by ditching the stock airbox and using less restrictive filters.
Sometimes those stock airboxes can be really restrictive, but you got to be careful with open filters, make sure you're not sucking in a bunch of dirt and water.
And the source actually recommended putting a little reed valve drain in the airbox to let water escape. Pretty clever.
It is. Now, for engines with fixed gearing, like carts, they often use pulse-type carbs.
How does those work?
They use the pressure pulses in the crankcase to pump fuel and meter it into the airstream. It's a good system for engines that don't have a gearbox to help them stay in the power band.
And they mentioned some specific tuning tips for those types of carbs, even detailing some mods for McCulloch cart carbs.
It's all about optimizing the airflow and getting that fuel-air mix just right. Now, finally, we got to talk about fuel itself.
Yeah, there's a whole world of racing fuels out there. Avgas, pump gas, leaded, unleaded, octane boosters, methanol, even nitro.
Each fuel has its own characteristics, its own octane rating, its own advantages and disadvantages, and you got to understand those differences to tune properly.
And they really debunk that myth that higher octane always equals more power.
Right. It's about matching the fuel to the engine's compression and ignition timing. If your engine isn't designed for high octane, using it won't make a difference.
Go, we've got the fuel mixed. Now we need the spark to light it all up. So let's dive into ignition systems.
This is where the magic happens, the spark that initiates combustion. And the timing of that spark, it's absolutely critical for power and efficiency.
The source talks about those old school points type ignition systems, the ones with the mechanical contact points.
Yeah, they were the standard for a long time, both battery and coil systems and magneto systems. They worked okay, but they had limitations, especially at high RPMs.
So that's why CDI, capacitor discharge ignition,
Yeah.
became the dominant system, right?
Exactly. CDI gives you a much faster, hotter spark, which is essential when those revs are screaming high.
They explained how the whole CDI system works. The capacitor, the trigger, the SER, the coil. It's pretty fascinating stuff.
It is. But they also mention some potential issues, especially with those automatic advance and retard mechanisms. If those get stuck in full advance, you can get some nasty detonation.
So it's always a good idea to double check the timing, even on CDI systems, right?
Absolutely. Now, some systems use fixed ignition timing, where the spark occurs at a set number of degrees before top dead center. But the optimal timing, well, that depends on a whole bunch of factors.
So type of fuel, the air-fuel mix, the compression ratio, the engine speed, even the spark plug position, it all plays a role.
It's all connected. Now, as the engine spins faster, you generally need more advance, meaning the spark happens earlier.
Why is that?
Because combustion takes time, so if the spark happens too late at high RPMs, the peak pressure won't occur at the optimal point, which is right after top dead center.
Ah, so it's like you're giving the flame more time to develop its full force.
Exactly. But too much advance can lead to pre-ignition and detonation, so it's a balancing act.
And thankfully, we have digital ignition systems now, which allow for much more sophisticated timing curves tailored to the engine's RPM.
Yeah, digital ignition is a game changer, and there are even programmable ignition boxes now, so you can really fine-tune the timing to your specific needs.
The source mentions something interesting, though, that modified two-strokes often need less advance, not more.
Right, because those mods usually improve combustion efficiency, so you don't need as much advance to hit that peak pressure at the right time.
Makes sense. And they gave a good tip for finding the best timing: start retarded and gradually advance until you find the sweet spot.
It's a solid method, and they emphasize that the optimal timing can change depending on the track, the weather, all sorts of factors.
So it's another area where you got to be willing to adjust and experiment.
Definitely. And the source really stressed the importance of having a good timing dial gauge for accurate measurements.
Because those standard automotive timing lights aren't precise enough.
Right. They're fine for basic timing, but when you're really dialing things in, you need that dial gauge.
And they even gave the formula for converting degrees of timing to millimeters of piston travel for those who like to get technical.
They covered all the bases. Now, another thing we got to watch out for is pre-ignition. That's when the mix ignites before the spark plug fires.
And that can lead to detonation, right?
Absolutely. Pre-ignition is often caused by hot spots in the combustion chamber, excessive compression, lean mix, too much advance, things like that.
So it's another reason to be careful with those timing adjustments.
Definitely. Now, they mentioned some specific types of spark plugs, like booster gap plugs, and recommended pinning them for high RPM engines.
Pinning, what's that?
It's basically securing the terminal nut so it doesn't vibrate loose at high revs. And they stress the importance of using the right spark plug reach and heat range for your engine.
Right. The reach affects where the spark occurs, and the heat range determines how well the plug dissipates heat.
Exactly. Too hot a plug, and you risk pre-ignition. Too cold, and it can foul up. Gotta find that Goldilocks zone.
So I think we've covered ignition pretty thoroughly. Now, let's get down to the heart of it all, the bottom end. This is where all the power gets generated, so those parts has got to be tough.
The bottom end takes a real beating. The crankshaft, the piston, the connecting rod, they're all under huge stress, especially at high revs.
And the source really emphasized the importance of precision when building and assembling the bottom end.
You can't cut corners down there. Everything's got to be measured and fitted just right. And they recommended talking to your machinist, making sure they understand the level of precision you need.
So what are some of the key things to check?